Dear students, today we are going to start our second class on electrostatics. In the first class, we studied about the definition of electric charge and its properties. So one basic thing you always remember that electric charge is that inherent property of a charged body by virtue of which one charged body will going to exert certain electric force on another charged body. Now the question arises, how much electric force will one charged body will going to exert on another charged body? So this electric force between 2 point charges, it was studied by Coulomb. So in today's class we will going to study about Coulomb's law and the related matter. So first of all, what does this Coulomb's law tells about? So it tells about the electric force between 2 point charges at rest. So dear students, here each word has their usual meaning. So what does it tell us about? Coulomb's law tells about the electric force between 2 point charges. So first thing, point charges. Second thing, when they are at rest. So to which charge we can call it point charge? The meaning is that whenever the linear size of any charged body is very less, we can say negligibly small as compared to the separation between two such charged bodies. In that circumstance, we can call that charged body as point charge. That is, linear size of charged body should be negligibly small as compared to the separation between two such charged bodies. Second thing, these two charged bodies should be at rest. So, as per Coulomb's law, how we can understand this? Let I have taken charge, first point charge as Q1, second point charge as Q2. Let I call, they are being separated by a separation of small r. Now, Coulomb's law states that the electric force between these two charged bodies, these are point charges and they are at rest. So, electric force between them, that is force F, will be directly proportional to the product of their charges, that is Q1 multiplied by Q2, while it will be inversely proportional to the square of the separation between these two charges. So 1 by r square. So Coulomb's law states that the electric force between 2 point charges at rest, when they are separated by a separation of r, will be proportional to the product of their charges, while inversely proportional to the square of their separation. Now, since this is a proportionality, so we have to make it exact equation. So we will write F will be equal to, so always we have to remove this proportionality sign by an appropriate constant of proportionality. So in my case, I have taken small k. Same thing, Q1, Q2 divided by r square. So this we can say is the simplest mathematical expression for so-called Coulomb's law. That is, force F equals K, constant of proportionality, Q1, Q2, product of the two charges, divided by separation square. So F equals K, Q1, Q2 divided by R square. Now the question arises, what should be the value of this K? So experimentally it was found that this value of K, it depends on two parameters. So first parameter is what? Which system of units we have chosen. Second thing, it depends on in which medium these 2 point charges are being placed. So for simplest case, I have taken system of unit as SI unit. So system of unit I have chosen as SI unit. Second thing, the value of K depends is medium. So medium I have taken simply vacuum, that I have placed these point 2 point charges in vacuum. So we can call it free space also. So SI unit I have chosen as system of unit, while I have placed these two charges in vacuum. So under these circumstances, when 2 point charges they are placed in vacuum and the system of unit I have taken as SI unit itself. So under that circumstance, value of this proportionality constant K, it will be equal to what? It will be 1 divided by 4 pi epsilon naught and will be mathematically equal to 9 into 10 raised to power 9 in magnitude. Now, what should be SI unit of this K? So, it is very simple to calculate the SI unit of K from this expression. So, to find out the SI unit of this K, simply we should know the SI unit of each parameters involved in this formula. So, left hand side force, that is SI unit will be Newton. Q1, Q2, it will be Coulomb into Coulomb. R square, it will be meter square. So, we want to calculate the SI unit of this K. So, it should be equal to what? Newton meter square divided by Coulomb square. So, that's why we can safely write Newton meter square per Coulomb square. So, this is the numerical value of this constant of proportionality K, that is 1 by 4 pi epsilon naught, and is equal to 9 into 10 raised to power 9 Newton meter square per Coulomb square. Here, the new parameter which we have introduced is this epsilon naught. So, what is this? This is nothing but the electrical permittivity. This is known as electrical permittivity of free space. So, actually, this parameter electrical permittivity, it depends, it is a property of medium. It depends on the medium, which medium we have chosen. So, in this case, we have chosen free space, that is vacuum only. So, this electrical parameter, sometimes it is asked what should be the physical significance of this electrical permittivity. So, this electrical permittivity, it simply tells about the magnitude of electric force between 2 point charges. It will going to decide how much electric force will be exerted between 2 point charges when they are being placed in a particular medium. So here, since we have placed the two charges in vacuum itself, so that's why we have to epsilon here 0, not simply it is denoting this free space or vacuum. So that's why this electrical permittivity, it is a parameter which is based on medium. This is a property of medium, and it decides the electrical force which is to be exerted between these two charges. So now, if we talk about the numerical value of this electrical permittivity in free space, so you can remember this. Epsilon naught will be equal to numerically 8.85 into 10 to power minus 12. If we talk about the units, so this is important thing. So units will be, since this is 1 by divided 4 pi epsilon naught, so that's why SI unit of electrical permittivity will be simply reciprocal of that of K. So that's why I can write it should be Newton inverse meter minus 2 and Coulomb 2. So this is the numerical value of electrical permittivity in free space. Now, so what we can modify here, force will be equal to 1 divided by 4 pi epsilon naught Q1 Q2 divided by R square. So this is another expression for Coulomb's law. When 2 point charges they are placed in vacuum and the system of unit which we are choosing is SI unit. So this K becomes 1 by 4 pi epsilon naught. So force will be simply 1 divided by 4 pi epsilon naught Q1 Q2 divided by R square. So students, till now we have dealt with the scalar form of Coulomb's law, but now its vector form is more important. So we will going to work out for vector form of Coulomb's law. So this vector, the name itself means now we have to take care of direction also. Till now it was just the magnitude of force, but now for vector form, to study the vector form of Coulomb's law, we have to take care of direction also. So for that I have taken the point charge as Q1, here Q2. Let I have taken for simplicity these 2 point charges, they are positive only, both positive. So they are separated by a certain separation small r. Now since both 2 point charges, both they are positive, so they will going to repel each other. So if we talk about the force on first charge due to second charge, so it should be repulsive in nature. Repulsive means where we are observing at this location, that is force on Q1 due to Q2. So simply I can write it at this point charge, force will be F12. So how we will going to read this? Force on first charge due to second, that is F12. So with this arrow mark I have mentioned the direction. In the same way on this Q2 second point charge, again both are positive. So on second charge, that is Q2, force will be exerted due to Q1, and again it will be repulsive only. Repulsive means if I am observing here, so this first charge will going to repel this second charge. So the direction will be, it will be something this. So I will write F21. How we will going to read this? Force on 2 second charge due to first, force on 2 due to 1. Now since in 11th standard you must have studied about, so as to mention the direction we use so called unit vectors. So here also that I call this direction I am calling as, this direction I am calling as R12 direction. So R12 cap I have written. Similarly this direction I have written R21 cap. That is R12 means the direction which is starting from 1 to 2. So that's why R12 cap. Unit vector means this is with cap, head cap. So R12 cap is here giving the direction from charge 1 to charge 2. In the same way, this R21 means the unit vector which is starting from point 2, it is going towards point 1. So these two directions I have mentioned, which I will be using for calculating F12 and F21. So now we can write F12 vector will be equal to what? So K times Q1 Q2 divided by R square. Till here it is scalar form, magnitude only. But since in the left hand side I have written vector, that is F12 vector. Force on first charge due to second charge, and that is with vector symbol, this bar sign. So F12 vector should be equal to K Q1 Q2 divided by R square. Now I have to assign the appropriate direction also. So here F12, this is, you have to think whether it is along R12 cap or R21 cap. So we are observing that this F12, it is going towards left. Same way this R21 unit vector also, it is going in the left side direction. So that's why it is appropriate to assign R21 unit vector. So here we have written F12 vector equals K Q1 Q2 divided by R square, and the direction will be from 2 to 1, this left side direction. So for that I have written R21 cap. In the same way F21, that is force on second charge due to first charge. So it should be again equal to magnitude will be same only q1 q2 divided by r square. Now we have to think about the direction. So F21, since the direction is right side, that is from charge 1 towards charge 2. So for this we have to use the unit vector as r12 cap. So we will be writing r12 cap. So here we have successfully written the vector form of this Coulomb's force, that is F12 vector, F21 vector. Now from the diagram itself, if we compare, see R12 cap and R21 cap, from this diagram what we are getting, that both these directions they are simply opposite to each other. So what we can say, R21 cap must be equal to negative of R12 cap. Since they are unit vector only, so their magnitude will be surely unity, that is 1 only. But direction we have to think about. So this R12 cap is going right side, R21 cap is coming left side. That's why these are simply opposite to each other. Now if we compare this F12 vector and F21 vector, you just think this whole stuff k q1 q2 divided by r square, this is simply common only. What is the difference? Difference is R21 cap here, but here this is R12 cap. So by using this fact, R21 cap, that is R21, this direction is opposite to this direction. So we can safely write that F21 vector, since magnitude is same only, it is common. So direction we have to think. So F21 vector is nothing but equal to, it will be equal to negative of F12 vector. Now you try to recall your previous knowledge that F21 vector comes out to be negative of F12. That is, force exerted on second charge due to first charge is found to be equal in magnitude but opposite in direction as compared to the force on point charge 1 due to point charge 2. And dear students, this is nothing but the Newton's third law. So what we can conclude here, that Coulomb's law, we started from Coulomb's law. We can say that Coulomb's law obeys Newton's third law. What we can say, Coulomb's law is obeying Newton's third law. That is, action and reaction, they are equal and opposite. So F21 is simply equal to negative of F12. So dear students, here now we can conclude about this Coulomb's law, that in scalar form Coulomb's law is equal to simply equal to force equals k q1 q2 divided by r square. If we think about the direction, that is vector form of Coulomb's law, so we have written F12 vector. So here we have to attach the appropriate direction with the help of so-called unit vectors. So what we have found, that this Coulomb's law, Coulombic force, it obeys Newton's third law. So these are the conclusion points, that Coulomb's law obeys, number 1, obeys Newton's third law. Second point, since we are observing that these two forces, F12 force on first due to second, similarly F21 force on second charge due to first charge, they are acting along the line joining between them. This is the line joining between them. So they are not acting like this or that. No, they are simply acting along the line joining. Correct? So that's why second thing we will call that Coulomb's law, Coulombic force is central force, central in nature. Correct? So these 2 points we can conclude, that this Coulombic force obeys Newton's third law. Second point, since these Coulombic force, they are acting along the line joining the 2 points charge. So that's why we will say this Coulombic force is central in nature. Now, so dear students, now we will going to start the next topic, that is dielectric constant. So on behalf of the knowledge of this Coulomb's law, what we have understood that I have placed the 2-point charges in vacuum Q1 and Q2, separation is smaller. So what we can say that the force between these 2-point charges, it should be F, I will write F vacuum, will be equal to what? It should be equal to 1 divided by 4 pi epsilon naught. So for this vacuum or free space, you must have to write epsilon 0 or epsilon naught into Q1 Q2 divided by R square. So this is simply the force between 2-point charges when they are separated by the separation of small r and they are placed in vacuum. So force medium is vacuum only. 1 by 4 pi epsilon naught Q1 Q2 divided by R square. I am calling this equation number 1. Similarly, if I say now I have placed these 2-point charges in a particular medium, so I will write now force will going to change. So we have to think how it will going to change. So instead of force in vacuum, I will write force in a particular medium. So F with subscript medium. So F medium will be equal to 1 divided by 4 pi. Now already I told you that this epsilon naught, this electrical permittivity, it is the parameter which is related to a medium, particular medium. Here when it was vacuum, I have written epsilon naught, but now I have replaced vacuum by a certain medium. So that's why now I will be writing epsilon only. Nothing. This 0 means for vacuum. Now I will be writing for any medium, I will just write epsilon. All other things stuff remain same. Q1 Q2 divided by R square. Equation number 2. Now what you do? Equation number 1 divided by equation number 2. So what we can say? F vacuum divided by F medium will be simply equal to, see these things they are common only. What is different here? Epsilon naught, here epsilon. So that only I am writing. So F vacuum, so it will be in the denominator. So here it will be epsilon naught. 4 pi factor is also common, it gets cancelled out. So epsilon naught in the denominator while epsilon will come in the numerator. So epsilon divided by epsilon naught. So now student, this ratio of electrical permittivity of any medium with respect to that of free space is given the name dielectric constant or relative permittivity. What we call dielectric constant or relative permittivity. So this is important expression, that dielectric constant or relative permittivity of any medium with respect to free space, with respect to vacuum, will be equal to what? It will be ratio of force between the 2-point charges when they are placed in vacuum to the force between the same point charges separated by same distance but in any medium. So that's why F vacuum divided by F medium will be comes out to be epsilon divided by epsilon naught will be equal to K or epsilon R. So this is relative permittivity. Now if we talk about the numerical value of this K, so dear students, this K will be always, capital K will be always greater than equal to 1. If we talk about free space itself, so this K will be equal to what? Instead of epsilon, it will be epsilon naught. Already here epsilon naught. So epsilon naught divided by epsilon naught will be 1. So if we talk about the dielectric constant, value of dielectric constant or relative permittivity, they are same thing. For free space or vacuum, so it will be simply equal to 1. For all other medium, the value of k will be always greater than 1. For example, if we take the case of water, I have taken the medium as water. So numerical value of this k is approximately equal to 80 or 81. So now you just use this value here. You come F vacuum divided by F. Now medium is what? Medium is water. So F vacuum divided by F water should be equal to K, and value of K for water is what? It is 80. So you write K equals 80. So that's why I can safely say that force in water will be equal to what? It will be equal to force, you do the cross multiplication, force between the two charges in vacuum divided by this factor 80 or 81. Okay, so from this relation it is very clear that the force between 2 point charges separated by a certain distance in water will be 1 by 80 times. Means it will be lesser by what factor? 1 by 80 times as compared to the force between the same charges when placed in free space or vacuum. That is the only reason whenever we put like anything in water, it simply get dissolved, because the electrostatic force between the point charges, between the charges of that material, it get reduced when we put that any material in liquid. So the electrostatic force between the constituent materials, charged particles, it get reduced by a factor of 1 by 80, and hence things get easily dissolved in water. Dear students, I hope the things related to Coulomb's law is very clear to you. So now we will going to work out some examples related to Coulomb's law. So first example we are taking is, let I call we have some two identical point charges, metal sphere, that is A and B. These are two identical point charge. So they are already charged. Let I call this is having charge Q, this is also having charge Q. What is given in the question? That we are bringing a third charge of identical size, but this is uncharged. So this is uncharged. Correct? Metal sphere A and B, they are charged equally. This is positive Q, this is also positive Q. But the third metal sphere, that is C, this is uncharged only. So what process we have to carry out? In first step, what the examiner is asking, that we have put this third sphere, that is C, in contact with A. In contact with this C, we have put in contact with A. A was already charged. How much charge? Positive Q. So I have put this C in physical contact with this A. So A is having how much charge? Q. But C is initially uncharged only. Now we have to think that how much charge they will be sharing. So this is one of the peculiar property of any metal or conductor, that whenever we are putting two or more conductors, metals or conductor, identical metals or conductors in physical contact with each other, then they will going to share the total charge equally. That is, if you talk about the total charge, so initially it will be Q for metal sphere A, 0 for metal sphere C. So total charge is how much? Q plus 0. So total charge is how much? Q only. Now when we have put them in physical contact, this charge will going to get equally shared. So that's why after this metal sphere A and metal sphere C. So since q plus 0, divide by 2. So we will write A take charge q by 2. Similarly, C also take the charge q by 2. Mean they are equally charged. In second step, what they are asking? So two identical metal sphere with charge qb1, C another one third metal sphere, it was uncharged only. In first step I have put this third metal sphere in contact with A and then replaced. I have made them separate from each other. In next step what we are doing, this C now we are putting in contact with B. So we will write B. So B, how much charge it is already having? It is having charge Q. So it is having charge Q. Now C is no longer uncharged. Rather it is having a charge of Q by 2. So here I will be writing, I have put this C in physical contact with B. So here charge will be Q by 2. So again use that property that whenever metal spheres they are put in physical contact with each other, they will going to share the electric charge equally. That is, now we have how much total charge? Q plus Q by 2 divided by 2. So this charge should be equally shared between these two metal sphere B and C. So after this what we can write here, that metal sphere B will be having charge how much? It will be Q plus Q by 2. So it is 3 by 2 divided by 2. So it will be 3Q divided by 4. Similarly, metal sphere C will be having same charge 3Q divided by 4. And sometimes what they ask, that calculate the Coulombic force, electrostatic force between metal sphere A and this final metal sphere C. So now metal sphere A and metal sphere C, let me have separated them by separation of small r. So here you have to think that A is finally having charge how much? Q divided by 2. Similarly, this C sphere is having now charge 3Q divided by 4. So force will be equal to what? Again same formula we will going to use, K Q1 Q2 divided by R square. So K Q1 is how much? Q1 is Q by 2. So Q by 2 into Q2 is how much? Q2 is 3Q divided by 4. So you write 3Q divided by 4. Divide by separation R square. So now you just multiply, simplify this. So the answer will be F will be equal to K times, this will be what? 3 divided by 8. K times 3 Q1 Q2 divided by 8 R square. So this is the final result. So students, now we are taking second example based on this Coulomb's law. So sometime what type of question they ask, that they will give us some two identical charges. We have two identical charges separated by certain distance, and they will ask that some third charge is to be placed between them. So find out the position, nature and amount of that third charge so that whole system becomes in equilibrium. So what is given to us, that first charge, let I call this is Q, second charge also identical one, they are separated by certain distance, let I call this is small r. This separation is how much? Small r. So what they are asking, that this is system of two identical positive charge Q and Q separated by certain distance r. What they are asking, that a third charge we have to place along the line joining between them. So at what position shall we put? What should be nature, that is polarity, should be positive or negative. Third thing, what should be the amount, so that the whole system it becomes in equilibrium. So let I call, I will going to place a third charge capital Q somewhere at a separation small x from this first charge Q. So that's why this separation will be how much? This total is R. I have placed this third charge at a separation of x. So this separation will be equal to how much? It will be R minus x. Correct? So now we have to calculate three things. That what should be the magnitude of this charge, what should be the type, that is the nature, and third thing, where we shall put this, so that the whole system attains the equilibrium. So we will going to use the condition that the whole system of how many charges, dear students? Total 3 charges. System of 3 charges attain equilibrium. So this condition we will going to use to obtain our this 3 type of different results. So let I call, first I want to find out the location, where exactly shall I put this charge so that the system it is in equilibrium. So here I am using that capital Q is in equilibrium, because since here already mentioned that system of 3 charges as a whole it should be in equilibrium. It implies that individually each charge will be in equilibrium. So that's why first, so as to calculate the position of this third charge capital Q, I am using the condition that this capital Q it is in equilibrium. Equilibrium simply means what? The net force should be equal and opposite. Net force must balance each other, must cancel out each other. So capital Q should be in equilibrium. So if all are positive, so this will going to repel this capital Q along this direction. This small q will going to repel this along this direction. So since capital Q should be equilibrium, we will say force on capital Q due to this small q should be equal in magnitude as the force on capital Q due to this small q. So we will write, let I call, so this number 1, number 2, number 3. First charge, second charge, third charge. So what condition I am going to use? That F31, that is force on capital Q due to small q, force on third due to 1, must be equal in magnitude as the force on third due to second. So F31 should be equal to F32. So you put the value. So F31 should be equal to what? K Q capital Q divided by 3 1. Separation will be how much? X. So K Q capital Q divided by X square will be equal to what? F32, force on third due to 2. So it will be again equal to K capital Q small q divided by. Now separation will be how much? It will be R minus X. So R minus X whole square. So numerator get cancelled out. What we can write here? X square will be equal to R minus X whole square. Now we simplify the result. What we will going to obtain? So I think you must have solved this. So how we can write? X square equals R minus X whole square. So both sides square, we can take square root. So one of the root we can write X will be equal to what? R minus X. And X, this side you bring left hand side, so it will be 2X will be equal to R, or we can say X will be R divided by 2. So first answer we have obtained, that at what position shall we put this third charge? At middle point, because this whole separation is R and this X comes out to be R divided by 2. So that this third charge Q is to be in equilibrium, we have to put it at a separation of R by 2 from either charge, that is at the middle point. So this is is one of the answer. Just try to understand this. So I hope this point is clear to you. We have calculated the position at which this third charge is to be placed between these two identical charges so that the whole system attains the equilibrium. So we have calculated x is equal to r by 2, that is right at the middle point we have to put this third charge. Now we will going to think about its magnitude. How much should be the magnitude of this charge so that the whole system should become in equilibrium. So first condition we have already used, that capital Q to be in equilibrium. All these three charges to be in equilibrium. So next condition which we will going to use is, let I call first charge to be in equilibrium. So let I call this charge number 1. Okay, this is in equilibrium. So again, equilibrium means what? Equilibrium simply means net force on this should be 0. That is, the two forces must get balanced with each other. Their magnitude must be same. So that's why force on this due to this capital Q should get balanced with this small q. So when it is possible, see, these two already they are positive. So this will going to repel this in this direction. That is F1, 2. F12 direction will be left side. Now how this can be balanced? Surely there must be some force which act opposite to this. So opposite means what? This is repelling this in this direction. Now capital Q will going to decide the direction if we want to have equilibrium here. So capital Q, the polarity or nature of capital Q, sign of capital Q should be in such a way that the force on this first due to third should be on right side. So when it can be, this is positive, so this should be negative. So this should be negative. Correct? So polarity should be negative. Immediately we can say that force on first due to third, it will be on the right hand side and surely it can balance this F1, 2. So this concept we will going to use for finding the magnitude of this third charge. So that is force on first due to third should be equal to force on first due to second. That is, we are using that this point charge Q located at point 1, it should get balanced, it should get equilibrium. So F13 K small q capital Q divide by, how much is the separation? Already I have calculated that separation will be equal to small r divided by 2. So I am going to use this result. So K small q capital Q divided by r by 2. This is the separation whole square. So again Coulomb's law is same, K Q1 Q2 divided by r square. But in my case Q1 is small q, Q2 is capital Q, and separation is how much? Small r divided by 2, and separation should be squared. Similarly, F12 should be equal to what? Again K small q. Q2 is what? This is also Q only. So K Q divided by, separation is how much? R square. So everything is getting cancelled out except, so K Q, here we will say capital Q R square 4 will be equal to small q R square. So R square also getting cancelled out, and we will be left with capital Q will be equal to Q by 4. Okay dear student, so 3 answers we have got for the separate cases. First, this capital Q is to be positioned at R by 2, that is right at the middle of 2 point charges. Second case, the polarity must be negative, because since it is given exclusively that system of 3 charges, they should be in equilibrium. Now this point charge, it can be equilibrium if and only if this third charge is negative. So polarity will be negative. Third case, amount, that is magnitude. This third charge should be equal to what? It should be either common charge divided by 4, that is q by 4. So these are the three answers. I hope these are clear to you. Thank you.